Okay, here we go. Question on combining normal distributions. So we go and read the main points here. There's two sizes, small and large. Distributions are independent, it means we can combine them without too many worries, and they have a normal distribution. Right, so I always like to start these by unpacking the information of the question and writing it in my main part, so I don't have to then keep referring back up to the question. And so clearly we've got some means and variances. All right, so let's go and write that as E of S equals 280, and let's put var of S here, which is 4. We know it's variance because you can see that it's given us millilitres squared. Okay, so that is definitely variance, and it's the usual way we denote normal distributions. The parameters in there are usually the mean and variance. And then let's go for the expected value of the large is 575, and the variance of the large is equal to 16. So that's pretty good. So what that means is we don't have to distract our brains by referring back to this section. We can concentrate all our energy and brain power on the questions, right? And we know that we're just going to refer to our notes on this little section here. So let's go ahead and look at part A. So one bottle of each size is selected at random, so that's a one large and one small. So I'm just going to go and write that down. One large and one small. So we've got a large and we've got a small. Find the probability that the large bottle contains less than 2 times the amount in the small bottle. So large is less than 2 times S. That's really clear that that's just one small bottle, right, scaled up by a factor of 2. So the way we do this is we have to combine those normal distributions into one. So we will bring everything over to the one side, L minus 2S, and that will be obviously less than 0. So I'm going to make another variable, let's see, the combined, equal L minus 2S. And now we want to find E of C and var of C. Alright, so that's key to this. Then eventually we're going to use the probability of L minus 2S less than 0, which essentially is the probability of C, the combined distributions, being less than 0. Alright, so it's quite a lot of things to process here. Alright, so let's go ahead and do that. Over here, E of L minus 2S, and here var of L minus 2S. Now the expectations we combine in the way you would expect it. So this is, if you want the full workings out, E of L minus 2 E of S, and over here var of L actually plus 2 squared the var of S. Now that looks unusual, a number of things unusual about that, of course, that even though we're subtracting, we still add the variances. And because this is one bottle scaled up by a factor, then it's not just 2 times the variance, it's 2 squared the variance. Alright, we'll see on part B where we just add the variances rather than square the number there. So let's go ahead and find the mean and the variance for C. So E of L, and this is where it's nice, isn't it, that we just have all of our information now in one place here. So we're only looking here and we don't need to cast our eyes back up here and get distracted. So let's try that. So E of L I can see is 575 minus 2 times E of S, and that gives me a value of 15, and variance of L is 16 plus 2 squared 4 times variance of S is 4, that gives me 32. So now always write out your final distribution. C can be modelled by a normal distribution, a mean of 15 and a variance of 32. And then what we're trying to do, of course, on here, we're visualising this combined normal distribution. 15 here, standard deviation is root 32, and then we reach straight away for our calculator. Let's move this out of the way. And this is an area. We want to find the probability that C is less than 0. So plop a 0 on, and we're trying to find that shaded area. So menu, probability, distribution, norm CDF. Lower bound is, negative infinity. Technically, these normal distributions go off to infinity, asymptotes. Upper boundary is 0, mean is 15, and the standard deviation, we can type it in straight away with a control x squared to get the square root of 32. Close the bracket, press enter, and yeah, it's a tiny value, and so the answer is 0.00401 to 3 sig fig, so a tiny probability. B now, we are using the same original details, and this time we're looking for one large bottle and two small bottles. Okay, so two small bottles, so this is a slightly different situation, right? Two small bottles is very different from one bottle selected and scaled up. Okay, there'll be less variability for two small bottles added together. So let's go and write that down. We want find the probability that the large bottle contains less than the total amount of the two small bottles. Now I'm going to put S1 plus S2 to indicate they're different bottles. So we are after P of L minus S1 minus S2 to be less than 0. Okay, and you could do this, right? Let's C this time equal L minus S1 minus S2. I suppose if you wanted, you could use a different letter. I'll call it B here because we had the we had C for part A. So let B equal the combine. So we need E of B and we need var of B. So E of B is just E of L minus E of S1 minus E of S2. Now you can clearly see that it's minus 2 of the E of S's. And then of course var of B, that's equals to the variance of L plus variance of the first small bottle plus variance of the second small bottle, and now compare this with part A. It's variance of L plus 2 times by the variance of S, whereas over here it's E of L minus 2 times E of S. Okay, so you can see that the expected value is going to be exactly the same. So that's pretty easy, right? So we've got this new E of B, this new distribution, which is the same as before, because we've already calculated that's 15, but the variance is a little bit different. So its variance of L, which is 16 now, plus only 2 times the variance of the small ones, 2, 8, that's 24. Okay, so you can see here that B can be modelled by a normal distribution, a mean of 15, and a variance of 24. Again, on the picture here, still centre about 15. It's a lot tighter though because it's root 24 here. Still want the 0 here, and we want this area. We switch to our calculator again, and we can go up. We can go up, up, grab it, and the only thing we need to change, of course, is that square root sign in the middle there, which is 24. So that speeds up the process. And here we've got the answer is equal to 0.0011. Okay, so that's part B done. And then if we have a little look at part C, I think part C is the easiest one of all, actually. So let's just get rid of this and we can have a look at part C. Part C is talking about a multi-pack, and a small bottle comes in a pack of 12. So let's let M equal multi-pack 12 times by S. But note this is S1 plus S2 plus ... right? Plus S12. Individual bottles, not one single bottle scaled up by a factor of 12. And we want E of M now, so E of M equals, well, that's just 12 times E of S, and var of M, that's just all the variances added together, which is 12 times the variance of a small. So E of M equals 12 times E of S, 280, right? And var of M equals 12 times var of S is 4. This one is 48. This one, if your brain doesn't work, switch to the calculator. 12 times 280. 3360. So the multi-pack follows a normal distribution. mean of the mean of multiply is 3360 millilitres, and the variance is 48. And we want the probability that M is greater than 3,400. So go ahead and draw your normal distribution. The mean here is 3,360. Standard deviation is root 48. We want this little picture here. There's 3,400. Reach for the calculator one more time. I'll go through the full menu. Menu, probability, distribution, norm CDF. Lower bound this time is 3,400. Upper bound is lots, so we can just put in a big number. I mean, technically, as long as we get maybe 4 or 5 standard deviations above the mean, then we're covered, because any area above that is so minuscule to the 5th and 6th decimal place. Mean is 3,360. Again, standard deviation, type it as a square root of 48. Close brackets, and there we go. So almost impossible, right? Almost impossible. Now, if we just think about why that is, this is 3.8 times 10 to the negative 9, so this is an almost impossibility. And there is a reason for that, of course, because the numbers we've chosen are quite interesting. So if we think about the square root of 48, I mean, this is approximately 7, right? 7 7's 49, approximately 7. Now we know the properties of the normal distribution. Within one standard deviation, so 3,360 plus 7, so that would be 3,367. This actually, from 3,360 all the way up to 400, that's a distance of 40, and that's about 6 of these, so it's almost 6 standard deviations. So you can see why that area here is so minuscule, because this particular point is almost 6 standard deviations away from the mean. Now we know within 3 standard deviations is 99.2 or 99.4%. So it's clear why this number is a crazy small number.